Hello guys, welcome to my video. In this video, I'll be talking about the parameters of the support vector machine. So I'll be talking about these parameters so that it can help you in the future to optimize your support vector machines when you're working with real-world datasets. So the first thing we are going to talk about kernels. So kernels are used to determine what type of hyperplane to use. And then we have the linear hyperplane, which is used in case of 2D data. Let's say if we have two features, let's say we want to predict what type of a flower it is based on the petal length and then the width and the petal length and the width. So in that case, if we have 2D data, it is good that we can use the linear hyperplane. And then in case of 3D and other dimensions, the RB, we can use the RBF and poly, which are nonlinear hyperplanes. So, and then we have the regularization parameter C. So C controls the trade-off between smooth decision boundary and classifying training points correctly. So so as you can see, if we have a small value of C, that means that if we have a small value of C, that means that our algorithm tolerates misclassified points. As you can see, we have two misclassified points here. And then if we have a large value of C, you can see that our algorithm will not tolerate misclassified points. As you can see, this as hyperplane tries by all means to classify all the points correctly. So how do you know what value of C to use? So the thing is, there's no like there's no certain value of C to use. The thing is, like you have to experiment. You can start with a smaller value of C, then you can start from a smaller value of C, and then you can increase the value until you find a specific value which improves the accuracy of your algorithm. And then we have the gamma parameter. So gamma defines how far the influence of a single training example reaches. So if we have a low value, that means that there is a far reach. And then if we have high value of gamma, that means we have a close reach. So the exact details of the decision boundary are going to be dependent on the points closest to it if we have a high value of gamma. So as you can see here, high gamma, only nearby points are considered. So if we have a high value of gamma, we are going to consider these points which are close to the hyperplane, and then we can ignore these points which are far away from the hyperplane. As you can, and then if we have a low gamma, which means that if we have low gamma, we are going to ignore these points which are close to the hyperplane, but only consider these points which are far from the hyperplane. And then we have the margin. So the margin is the separation of the line to the closest class points. So a good margin is one where there is where this separation is large for both classes. So as you can see, a good margin is a margin which is equidistant from both classes. So as you can see here, we have this blue data set, and you can see the distance from the hyperplane is almost the same as this from this black from this black data set to this hyperplane. And then you can also see these points are equidistant. But as you can see here, we can see that the margin is very close to the blue class. At the same time, the hyperplane is very close to the blue class. At the same time, it is far away. It is far away from the black class. So as you can see that this sort of margin is almost like it is sort of like biased. As you can see that it is close to the blue class. At the same time, it is far away from the black class. So the next thing we are going to do is we are going to visualize these parameters of the support vector machine using a real world example. So in this code, I've imported NumPy, which is a mathematical library for performing mathematical operations. we have the matplotlib, which is also used for data visualization, as we are going to be visualizing different types of kernels and other parameters. I've also imported the support vector machine from the scikit-learn library, and also I've also imported the dataset. So in this line, I first imported the iris dataset. So and then the first thing is I've selected the first two features, as you can see from this one, which means from 0 up to 2. So I've imported the first two features, which is these are our features, the x features, and then we have the target value, which is y, is equals to iris.target. And then the next thing is I have this function, which is going to plot different parameters of the support vector machine. So let's run our code. So here we have kernels. So as I have said, like the kernel parameter, like select the type of hyperplane we are going to use. So using linear, we'll use a linear hyperplane and a line in case of 2D data, and RBF and poly uses a nonlinear hyperplane. So as you can see here, I've 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 defined my kernels in sort of like an array, and then we are going to look through each of the kernels in the array, and then we are going to display the kernels using the plot support vector classifier function we have created above. So as you can see that the linear kernel is sort of like a line, sort of. And then as you can see that the RBF is non-linear, as you can see that it's curved. And then the poly also, you can see that the poly is also a non-linear kernel. And then the gamma parameter, the gamma is a parameter for nonlinear planes. So we only use the gamma like when we are working with the RBF and the poly kernels, but we don't use it when we are working with the linear hyperplane. So as you can see that low values of gamma considers points which are far away, and then high values of gamma consider values that are close to the hyperplane, as you can see. So increasing gamma may also lead to overfitting, as the classifier will be trying to perfectly fit the training data. Also, the other thing is because the value of gamma will be high, the model will be sort of like complicated, and then if we complicate our model, it will be very difficult for our algorithm to sort of generalize to the dataset, which also leads to overfitting. And then, as I've said, like the C parameter is the penalty parameter of the error check. It controls the trade-off between a smooth decision boundary and classifying the training points correctly. So here I've defined the different values of C, and then we are going to look through them, and then we are going to plot them using the plot SVC method we have created above. So as you can see that low values of C, like low values of C, low values of C tolerate misclassified points. But as we increase C, you can see that we'll be trying to fit all the data sets perfectly into the hyperplane. So this also may lead to overfitting, as this will complicate our model, which will be difficult for our model to generalize well to the data set. And then we have the degree parameter, which is used when the kernel is set to poly. So it's basically the degree of the polynomial used to find the hyperplane to split the data. So as you can see, this is the degree. So as you can see, if the degree is like if the degree is low, it's almost the same as setting the kernel to be a linear hyperplane. So as you can see, using a degree of 1 is almost the same as using a linear hyperplane. So thank you for watching, guys. I hope this video helped you a lot understand the parameters of the hyperplane. So if you have any suggestions, please leave them in the comment section below. And also please subscribe to my channel and also click on the notification bell so that you don't miss any of the videos I'll be releasing you, helping you to learn machine learning. So thank you for watching, guys.